With the Department of Natural Resources. Some of you might know her, and she is the lake monitoring lead. She's the lead of the monitoring program at the DNR. So with that, I'm going to turn it over to Katie, and thanks again for being here.
Well, thanks a lot for inviting me. Yeah, and also I'm the chair of the Water Resources Working Group for the Wisconsin Initiative on Climate Change Impacts. Has anyone heard of WICI before? Yes, a few of you have. So what I'm going to do today is talk about a variety of different things. A lot of it comes from my role with WICI, but then a lot of it also things that we're working on at DNR. So I just wanted to start with this quote by Paul Pullman saying that climate change is sometimes misunderstood as being about changes in the weather. In reality, it is about changes in our very way of life. These are pictures of my family. My family's from Wisconsin. My dad grew up on Lake Wabisa, just south of Madison. My mom grew up in Racine, going to Lake Michigan. My sister and I grew up here, and then spending time up north on a lake called Lawson Lake. So for us, yeah, this Wisconsin landscape and the water here, it really is a part of our way of life. And indeed, it is changing. You can just look at the news and look at the pictures and see whether it's the coastal erosion along Lake Michigan, some of the flooding we saw. This is actually Lake Wabisa. I live down by Lake Wabisa now. And then, some of the flooding, and then some things that are maybe less visual than these extreme storms. Something like walleye, which is a really traditional fishery in Wisconsin. They're adapted to cooler temperatures, and we're seeing declines in their recruitment and overall declines in the fishery. And another thing I just want to point out today is, as I'm going to be talking here, I'm going to talk a lot about impacts of climate change to Wisconsin's waters and particularly the lakes, but I'm also going to be talking about adaptation. And one sort of point I'd like to pose here, and that I've been thinking a lot since joining WICI, is not only should we be doing science on what are the climate impacts, but how can we do science to inform our adaptation strategies? So I'd like to be thinking more about climate adaptation science as well as climate impact science, which I think is something we tend to do more of. So today I'm going to talk about sort of two threads here related to climate change. One is kind of focusing on how rising temperatures are affecting our lakes and maybe some of our other aquatic ecosystems. And then the other one is more about the changing precipitation. Now, are some of you kind of familiar with, I decided to skip this, but familiar with the types of changes in climate that Wisconsin is experiencing? Yeah. What's one that you think of?
More rainfall in the summer.
Yeah.
And more, really intense rains.
Yeah, more intense rains, warmer overall. But yeah, Wisconsin's kind of getting warmer and wetter and expected to get warmer and wetter. So let's get into the warmer side of things. Lake Mendota, just over here on campus, is one of the most studied lakes, or maybe I can just say the most studied lake in the world. And we actually have a really long ice record on Lake Mendota, so about 150 years. And you can see that the ice cover duration has declined by about a month. This year, this is not an updated graph yet, but 2024, we had 44 days of ice cover. So you can see one of the lowest, although the lowest on record it looks like was in 2000. And a lot of lakes in the world are showing this same pattern with reduced ice cover. This is a projection for ice cover duration in the Northern Hemisphere by 2050. You can see this is the global projection. So the black areas are places in the world that will still have winter ice cover every year. But then you start getting with these, no matter how much warmer. And then like red here is if there was an 8°C increase, these would still have, let's see, this is where you start to see changes. So in any case, like orange right here is intermittent ice cover right now. So you kind of see already getting into Wisconsin. Something like Lake Geneva, some of our biggest lakes have already had some winters in which they didn't get ice on them. And so by 2050, we see that we predict a lot of these southern Wisconsin lakes won't be ice covered anymore, which could have, you know, huge ramifications ecologically and recreationally. I also want to talk about just the water temperature. Dick Lathrop has looked into some of the long-term temperature records. So Wisconsin, there's a long-term ecological research sites. There's several lakes in northern Wisconsin and here in the Madison area that UW-Madison Center for Limnology has been studying. And so again, you see this record on Lake Mendota going back to the late 1800s. And you can see significant increasing surface water temperatures in both Lake Mendota and in Trout Lake. This is what we see, of course, is through the seasons. The surface water temperature will warm up and then cool down, of course, again in the fall. So what Dick did was try to come up with some specific points in time. So here, using the September 1st as a metric to look at, so that that seasonality effect is consistent, and you could look at the trend over time. I will say that not every month is significant. So on Lake Mendota, if I were to show you the August 1st date, it wouldn't be significant. Or sorry, I think it's July for Mendota. On Trout Lake, if I were to show you the August 1st metric, it wouldn't be significant. So some of the months are showing significant trends and some aren't. I kind of think when I'm looking at this that, we know we're seeing a longer or a shorter ice cover duration, and then you kind of see warmer temperatures in the spring and fall. One thing that was interesting with Dick's work is that he also looked at the maximum summer water temperatures, and that's not increasing. But these temperature sort of patterns, of course, they are really important for a lot of different aspects of aquatic ecosystems, and I'm not even going to go into all of them just because we only have 45 minutes. One thing I wanted to talk about was just the physical effect on dissolved oxygen. This is something that I worked on with Steve Jane. Steve did this big project gathering data from places like DNR, Wisconsin DNR, but a lot of other researchers and state agencies, national agencies all across, well, not the entire world, but you can see through Europe, even New Zealand, and then a lot of the United States and Canada. And basically found that we're also seeing, while we're seeing these warming temperature patterns, we're also seeing declines in dissolved oxygen in our lakes. And so I'll just kind of talk you through this. This graph on the left, this will show you the temperature trend in all these different lakes. And so you can see, yes, in this analysis, this is from 1980 to 2017, surface waters are warming. You can see that the deep water, so in that hypolimnion where, when lakes stratify, you have colder water on the bottom, that deep water is not warming. That's centered, the mean here is centered right around 0. But look at then the oxygen trends. You can see here's the 0 mark, and you can see that the top of that bell curve is on the negative side. So oxygen declines in both the surface waters and the deep waters. One other thing to note though is look at that distribution, it's really wide. And so you have, at the same time, even though most lakes are showing this declining trends, you have some that are increasing in their oxygen concentrations over time. And so, yes, there's a large variation between lakes, and then dissolved oxygen declining overall in most lakes. Now, we submitted our data from Wisconsin DNR, and also like I said, the long-term ecological research, they submitted data to this project too. So if you look at the Wisconsin lakes, this is showing you that we have the full range of trends in our lakes. Some lakes that are showing strong declines in oxygen, and some that are showing strong increases. So basically from the lowest to the highest part of the range, we see that, but we also see that most of them are near 0. I wanted to just show you this in terms of a map, some of the lakes that actually have long-term records that were used as part of this study. So this is southeastern Wisconsin. Here we are. Here's Mendota, Wingra, and Monona. What I did is just stacked the two squares on top of each other. So on Crystal Lake, This means the surface water, the top square has an increasing dissolved oxygen trend, somewhere between 0.05 and 0.5 milligrams per liter per decade. And then the deep water shows no trend. So you can see a lot of these southeastern Wisconsin lakes are showing increasing oxygen trends over time. Mendota, these Madison lakes, are showing declining oxygen trends. Fish Lake, which some of you I know on campus here are studying Fish Lake, an increasing oxygen trend on the surface, but a decreasing in the hypolumian. So this kind of study, is just gathering all these long-term records from around the world and trying to see what's been happening. But they didn't really look at mechanistic explanations for these trends. That's kind of the next step. But what I told you before, that the water temperature is warming. So a lot of the declining oxygen trends that they found in the surface waters could really be explained by that warmer temperature. That alone could explain it, just because there's lower solubility for oxygen in warmer water. Another explanation is particularly looking at if there's negative trends in the hypolumian, is this long idea of, okay, so ice off comes earlier, then the lake will stratify earlier in the spring, so then you have a longer stratification period. That means that cold water on the bottom there'll be more respiration for a longer period of time, and in that case, then less oxygen remaining. So that could be another explanation for the declining DO. One of the hypotheses as far as why we would have increasing oxygen in some lakes is that we are also seem to be seeing more cyanobacterial blooms. And when you get the cyanobacteria, they can, obviously through photosynthesis, produce oxygen. And so maybe, especially in these southeastern Wisconsin lakes where we have high nutrients, the warmer, nutrient-rich water might be fueling more algal blooms and leading to higher oxygen. That's still just a hypothesis, and so down here I'm kind of pointing out, I think some of the next areas of work for us are to do more research and looking at mechanisms driving these trends, monitor the phytoplankton communities over time along with the oxygen. So, and this also just points to the importance of continuing our long-term monitoring. So, at Wisconsin DNR, all these lakes here are lakes that we've been monitoring every year. A lot of them since, I think we're up to over 30 years for a lot of those, and then, our long-term ecological research sites monitored by UW. Okay, now I'm going to transition a little. So we've got temperature, we've got oxygen. This is important for the biology of the lake. And I'm going to highlight this in particular for something like a cisco, which is a fish that lives and needs cold water. This is a lake fish. There's other fish like whitefish and lake trout that live in lakes and need that cold, oxygenated water. So one thing when we start thinking about climate change and then how do we adapt our policies to make sure to protect some things like cold water fish, who could be threatened by both warming temperatures and declining oxygen, is to develop criteria to make sure we have that good oxythermal habitat. So I'm going to just walk you through this diagram. This green here is trying to signify good oxythermal habitat for cold water fish. So the temperature is cold and there's plenty of oxygen. We're defining that as having at least 6 milligrams per liter of dissolved oxygen. So in the spring, when the lake is mixed and the water's still just warming up, usually there's plenty of good habitat for them. It's cold and plenty of oxygen. And the summer, the sun starts heating up the surface waters. You get the thermocline here, and then colder water at the bottom. Well, so warm and then cold. This is showing the oxygen concentration. That's funny, it's going kind of in a weird direction. So this is from our water quality standards booklet. But so here's the 6 milligrams per liter that we're on the target. We want to have more than that. So usually you have a lot of oxygen near the surface, and then as you have more respiration down the bottom, you start to get this deoxygenated condition down here. So for something like Cisco, we want at least 6 milligrams per liter of oxygen, and then colder water. And so you can kind of in this particular figure, we've got still enough oxygen in that kind of metalemnian or below the thermocline area. Now, we just actually adopted these standards about a year or two ago, and what we do is we require that this depth from the top to the bottom should be at least 1 meter thick. And it's just a number, but basically the idea is trying to protect that habitat. So that was actually kind of a big step forward for us to actually put something on the books with our water quality standards to protect these species. Now, what would we be able to do if we're not meeting it? So I just want to talk a little bit about how phosphorus can relate to this. So phosphorus is a nutrient that come into lakes and fuel that respiration, right, that would use up oxygen. And so we have phosphorus standards also as a water quality criterion for lakes in the state. And we actually have lower phosphorus standards for lakes that have cold water fish. Again, trying to keep that good water quality with high oxygen. So thinking about climate change and trying to protect these species, let's say some lakes are going to have good future habitat no matter what. They're deep and really high water quality, a lot of oxygen. It really won't have much effect, so we just maintain the phosphorus standard. Now let's think about some lakes where maybe the future habitat is at risk because of climate warming. Maybe some of these lakes might not be quite as deep, and so the fish really need to have good oxygenated water in the deep area. And so here we could think about maybe lowering the phosphorus standard or trying to work in the watershed to protect, keep like forested watershed and protect it from runoff and getting more nutrients coming in. And I'll just pause here and say this is one example of this is on Lac-Courte in northern Wisconsin, where there has been some fish kills and kind of this overall concern of greater risk to Cisco and whitefish over time. We also saw that there is a warming trend in the surface waters on Lac-Courte. And just recently, about a year ago, we adopted a lower phosphorus standard than what we already had, even lower than the lowest standard for the cold water fish. And then, of course, there might also be some lakes where just persistence is unlikely. Like even if you lower the phosphorus and protect the watershed, it's just a shallow lake that's warming up, and so it's not going to provide good habitat for Cisco in the future or other cold water fish. This is something, again, sort of DNR lingo, but we could change the use designation. So basically, we say, no, we don't have an expectation for cold water fish to live here anymore. So instead of an expectation of 15 micrograms per liter phosphorus, we'll allow for a higher phosphorus standard. Now, this is all just sort of theoretical. It's not something that we're doing now, but I think it's something that we're going to be faced with as we go into the future. And Lac-Courte is an example, where we've already kind of dealt with that. This is also just kind of highlighting the fact that there are tools out there and more tools that I think we could be using to try to think about adaptation and looking at the vulnerabilities of different lakes. So here's Trout Lake. This is the Midwest Glacial Lakes Partnership has this conservation planner, so it's this interactive mapping tool you can go on. And so I selected Trout Lake here, and then it says, what is the climate vulnerability? Oh, it's high. And it says, looks at the suitability of Trout Lake for different fish species, and this is using projected future water temperatures to try to determine what the future vulnerability would be. So you can see, I don't know if you guys can see this very well, but there's 4 species on the bottom here on the left of fish: bluegill, northern pike, walleye, and cold water species. So on the current condition, Trout Lake is suitable for them. But then this is over here for 2050 is showing that cold water species, again like our lake trout or Cisco, their survivorship in Trout Lake is unlikely. So that just is something that people could use and select whatever lake they want and kind of look at that and try to think about what would they want to do in terms of management actions in that case. And so this is sort of just a call to develop more of these interactive tools. Yeah, I kind of glossed over this, but USGS has done a lot of modeling to hindcast water temperature in lakes and then forecast it into the future and making that more accessible for people to use in interactive tools like that so that they could then do planning work that would be really helpful. And then I think another thing is just recognizing that not all lakes are a little bit different. So when we think about adaptation strategies and climate vulnerability, like we'll really want to be tailoring our management actions to each one of those. All right, so now I'm going to transition away from temperature and talk a little bit about the precipitation side of the story. So around 2010, trout, or this is in northern Wisconsin, actually this is a picture from Little Rock Lake. There was a drought in northern Wisconsin. A lot of the lakes became really low. You can see all this stranded woody habitat. Usually the lake shoreline would have been up here somewhere. And then you can see, like fast forward, 8, 9 years, maybe were some of you on campus during this time when Madison, the isthmus was really flooded. And so we're seeing these highs and lows. And this is, I'll just kind of step back and say this is really a natural part of the lake cycle, and particularly on seepage lakes. Seepage lakes don't have a river going through them, so they're really more sensitive to changing precipitation. This is a graphic just showing you how the plant communities shift with lake levels. And so when lake levels rise, you have kind of more aquatic plants going inland toward the land. Your terrestrial plants would get flooded out and kind of die back. And then when lake levels fall, more terrestrial plants and kind of these beach species can then migrate toward the lake. And so you kind of get this ebb and flow and shifting of plants. And you have some things like, this is a depiction of Fassett's local weed, which is a rare and threatened species. They really depend on that fluctuation because they actually colonize in the sandy areas when the water level recedes. And they just do their whole life cycle in that short period of time during a drought. Some other species too, like bulrush, really need that dry period for their seeds to germinate, but then they need the water to come back up and live as sort of emergent plants in the shallow water. So all of this is just to say that this is that Fassett's local weed that's colonized all of the stranded kind of inland or nearshore area of the lake bed. You can see in this one, these are tree saplings. This is during a high water phase, and so you can see how if the lake levels stayed low, they would become big trees, but because now the waters have come up again, that's keeping those terrestrial species back. So this fluctuation is important for maintaining ecosystems, but then we also know that the floods and the droughts have a lot of ecosystem impacts as well. And so I'm not going to talk about all of these. I'm going to get into more detail on the clarity side, but just wanted to mention that these are all different sort of responses that have been associated with lake level fluctuations. So one is mercury bioaccumulation in walleye. Kind of after the high water phase and the lake levels go down, that's actually been associated with acidification in the lake, and then mobilizing and the methylmercury cycle. So that's kind of a real complicated and interesting one. Of course, there's some more obvious ones of just concerns of property damage during flooding, sometimes septic systems getting flooded, recreational impacts. So here, you see this stranded dock far from the water during a low water level time frame. This was from Sparkling Lake, one of the LTER sites, where there may be some interesting combinations with rusty crayfish, which is an invasive species. The cobble being stranded during the drought. Cobble is an important area for them to hide when they've got their juveniles. So less recruitment for rusty crayfish possibly during the drought. And then also some studies that have been done again in the north with looking at this woody habitat as being really important for fisheries, providing kind of shelter for the prey fish and really shifting the dynamics between largemouth bass and yellow perch during that drought phase when that habitat was stranded up above the water line. So I'm going to just talk about the water clarity effect a little bit and point out that it's pretty interesting because you can have an opposite effect of lake levels on water clarity depending on the type of lake you're in. So here, I'll just show you a eutrophic lake, which is a lake that has more nutrients in it. Those tend to get clearer when lake levels are higher. But in oligotrophic lakes, or really clear water lakes with low nutrients, the opposite effect occurs. So at higher lake levels, the water clarity declines. So I'll show you this with some data. So this was a project that I did with Peter Lisi, who was a postdoc at UW at the time that he did this analysis. We were looking at lakes in northwest Wisconsin. Shell Lake in northwest Wisconsin has a really long-term lake level record. A lot of lakes don't have a long lake level record. So we use that as a proxy for all the lakes in the area. And you can see that around 2003 was that high water phase, and that drought I told you about over on Little Rock Lake around 2010. You can see that was a lower water phase then. So let's look at the oligotrophic lakes. Here's a few examples: Silver, Beaver Dam, and Stone. And you can see, well, you've got this hill shape here. You've got a valley over on these lakes. So around that same time in the early 2000s, when lake levels were high, you can see that water clarity declined. So this is showing water clarity, a negative response here, so lower water clarity and all those. Now just look at the patterns on the lakes, these eutrophic lakes on the left side. You can see that it's also more of that hill shape corresponding in time with this higher lake level leads to better water clarity. Now, I mean, one thing to point out is, of course, the eutrophic lakes are always kind of not very clear, and the oligotrophic lakes are still overall more clear. But we're seeing opposite effects of the same physical driver. And so some of the reasons this might be occurring, on the oligotrophic lakes, thinking about more rain leading to more runoff and bringing nutrients into the lake that can fuel algal blooms, or just bring in sediments and make it more turbid. That's kind of what we think is happening in the oligotrophic lakes. USGS has studied Silver Lake a lot, and that matches up with some of the other data they have there. On the eutrophic lakes, if you start reading into the literature about drought and the effects on water quality, here it's more of a dilution versus concentration effect. So basically, without the rain, you're increasing the residence time and just kind of stagnating the water and giving that, with maybe warmer water, also the chance for cyanobacteria to grow and other algae and just sort of concentrate. And I think that's probably what we are seeing here. But again, these were actually data collected by our citizen lake monitoring program, so all volunteer data, and we don't necessarily have all of the other information on these lakes to go with it, to like confirm that it's really higher chlorophyll or something. Okay, so that's just one example of the effect of lake levels on lake ecosystems. Now I'm going to just talk about lake levels for a little while. So like I mentioned, we don't have that much lake level data on many lakes in the state, especially not many long-term records. This is Anvil Lake over in Vilas County. Of course, you can see here we have a nice, really long-term record there. The black dots are the observed lake level values. I did a project with, you can see the co-authors on the bottom here, Noah Lodig and others, to try to develop models to predict lake level variation, because we can see that it's an important driver for a lot of other things. And so this is the blue points here are our model results of lake levels, and you can see it's doing a pretty decent job at simulating, at Hein casting lake levels on Anvil Lake, maybe over predicting the height in the early 2000s there. This is a really simple model, and this concept really came from Bob Smale, who was also trying to model groundwater level fluctuations over time. And really the only predictor is this 8-year cumulative deviation in precipitation. So the idea is that with a single rain event, you've got a lake is a big volume of water. You get a single rain event in a small stream, you might really see the stream flow increase that same day. But in a lake, it's got this memory and this big volume, so it takes a lot of water to actually bring up the lake by an inch. So what this is saying is we're going to look at the 8-year cumulative deviation, so how different it is from the average, like summed up over 8 years. And when you start to have higher than normal rain year after year for like 8 years, then you're starting to see these lake levels go up. Or vice versa, if you're having less rain than normal year after year after year, that's when you start to see them go down. And overall, if you look at lake level patterns over time, you see more of this decadal cycle, longer term changes, not kind of the flashiness of streams. So that was the main predictor we used, and then we gathered lake level data from all of the state. We went into the archives and DNR and paper records that we had, USGS records, UWs, everywhere we could find it. Each one of these numbers here is plots that's a different lake, and we're just showing you the regression basically that shows the cumulative deviation in precipitation on the x-axis and the lake level anomaly on the y. And so you see some pretty good fits here. Like this is a pretty decent predictor for figuring out when lake levels are going to be high or low. But one thing that you might notice is that the slopes are pretty different between the different lakes. So the mean slope is 1.2, but the range is 0.5 to 4. And so what this is kind of saying then is, okay, overall the lakes, you could say they're all going to be higher or lower based on this, but some are going to be more sensitive to the changing precipitation than others. And so then we also tried to develop a model to predict the slope and be able to say, well, what characteristics would make the lake more sensitive and respond, with more dramatic changes in lake level than others. And so this was the best model. It's the elevation difference, so to explain that a little, what we were looking at is where does the lake sit in the landscape? And so if it's kind of perched high in the watershed or low compared to its watershed, that could have a bigger effect. So when you have a bigger difference, then like a seepage lake that's high in the landscape compared to the whole watershed, that can have a bigger difference. The percent cover of the forest in the watershed, and then the Darcy, that's giving you kind of an indicator of the soils in the watershed. So that explains like 50% of the variation in slope, but there's still kind of a lot left. So basically, I think, if you don't have a lot of information, we're pretty good at predicting when the highs or lows would occur based on the precipitation record, and then we could tell you which lakes might be more sensitive or less, but then there's still going to be some variation that we can't timecast very well. Then I want to talk a little bit about trying to define the lake level regime. So thinking about in streams, we talk a lot about the flow regime and looking at the flooding, how big the river will flood and how often. We want to do something similar for lakes and looking at these long-term records. So this is Devil's Lake, and you can see that has another long-term record. And we are describing the lake level regime with 5 metrics following what streaming hydrologists do on streams. One is to just look at the magnitude. So these are exceedance probabilities, and we can say, this black line is a 50% exceedance probability. So usually that's, the average for where Devil's Lake's lake level occurs. And then you can do some higher ones, like this would be the 10% exceedance probability. So the high water levels that only get exceeded 10% of the time. Then we can look at something like frequency. So here, 30% of years have more than 1 month above this infrequent high. And then something like duration, so how long, if it gets that high, how long does it last? And usually about 3 months. Then we can also look at things like rate of change. So on a monthly basis, the lake would go up or down by about 0.4 feet. On a seasonal basis by about a foot, and on an annual about a foot. And then also we can look at timing. So this is showing you seasonality, and that Devil's Lake tends to be higher in the summer and lower in the winter. Now I'm just going to show you Devil's Lake to keep time moving, but when you start doing this for other lakes where we have long-term records, you can really see some differences between them, like the timing could be really different. It's interesting to see lakes with dams where you can see that the peak is truncated because they're letting the water out, but then you can also see ones with dams where they actually can't let it out, so you still get that flood effect. They can't let it out fast enough. So all of this is to say, like, here's ways that we can monitor lake levels over time. We can have metrics to describe it, and this is going to be really important for us to be able to monitor and be able to see how climate change is affecting lake levels in the state, and then what that means for the ecology. So kind of this is where I'm going next in my head is what will be the effects of climate change on lake levels, and we can think in terms of these magnitude things, the average, high, and low. We know, looking at our historic data, we know what the lake level regimes have been on a lot of lakes in the state. Well, quite a few, not a ton. And then we want to know, what will it be like in the future? Do we expect, because things are getting wetter, that lake levels will go up? Or maybe also because it's getting warmer, and that could lead to more evaporation. We also know that there's less ice cover, which can also lead to more evaporation. Maybe they go lower. Maybe more extreme because of these extreme rain events we're seeing, but maybe the opposite could be true. Really, we don't know the answers at this point, and I haven't seen projections for inland lakes. Michael Notaro, I know from here, has been working on that for the Great Lakes, and I think that's one of an interesting scientific question for us going forward, is trying to do similar work to look at what the future might hold for inland lakes. Now I'm going to shift gears a little bit away from climate change to talk about a little study that we did. Well, it was a really big, expensive study, actually, looking at this lake level stuff. And basically this dates back to 2017 when the legislature put in this 2017 Wisconsin Act 10. Are any of you familiar with sort of the groundwater pumping used for irrigation in the central part of Wisconsin? So yeah, there's a lot of irrigation there to grow crops like potatoes and other crops. And there were concerns by some that this pumping was leading to dried up streams and dried up lakes. And so the DNR was tasked with determining whether, and this is specific language from the bill, whether existing and potential groundwater withdrawals are causing or are likely to cause a significant reduction of the navigable lake's water level below its average seasonal levels. And I highlighted in red this significant reduction part and also this average seasonal levels because there was no definition there, and there's kind of different ways you could interpret that. But at the same time, it was kind of nice because then we could, scientifically decide what made sense in terms of how to interpret that. So we were tasked with determining this for 3 specific lakes, and I'm just going to walk you through sort of the final results rather quickly here. But I've already given you this backdrop of lake levels vary over time. So here's Pleasant Lake and here's Long Lake. We also studied Plainfield Lake, but I'm just going to show you contrast these 2 lakes to give you a sense of it. So the first thing was, okay, what is the natural lake level regime for these lakes, and what would it be without groundwater pumping? So here is a modeled Hein cast of lake level elevations on the 2 lakes over time. And this was, again, using precipitation data and a groundwater flow model. And we were trying to not put specific years in. This was really just trying to say, given the climate, this is what kind of variability we might see with climate alone. Then, I already explained to you about these exceedance probabilities, so we were able to define the lake level regimes. So something like Pleasant Lake varies by about 3 feet, and that's 80% of the time. So, 80% of the time is kind of in this blue band. And Long Lake is shallower, but it actually varies a lot by almost 6 feet, 80% of the time. So we have that as our backdrop. And then we ran some scenarios about if you change the land cover and make it, more agricultural land cover, and then do the pumping scenarios given like real pumping records, what would be the effect of irrigated agriculture? And so the blue line is just from climate alone, and then the yellow line is showing you the lake levels with irrigated agriculture. And so you can see on Pleasant Lake that the magnitude went down by 0.4 to 0.5 feet, and on Long Lake it went down by like 2 to 3 feet. And one thing I can also mention to you is you can see that the two lines kind of mirror each other, and so basically the lake levels were going down even in the highs and the lows. When we first started the project, there was this sort of theory that maybe the lake levels would go down during the lows only, but like during drought, but not during the highs. But so basically the aquifers come down overall. So here's an example for a Long Lake. You can see the average lake level. This is kind of how we communicated this out with the stakeholder groups. Then you can see that the lake level would vary from high to low. This is the actual profile of the lake. So you can see it's a shallow lake, so low level is really not very much water in the lake anymore. So that's the natural lake level regime, and we can put that to the side. Then we saw we looked at a number of different ecosystem impacts, from fish to aquatic plants to recreational uses. And so we determined that if the lake level just went down a little bit on Long Lake, which is really sensitive because it's so shallow, that would you could only take it down a little bit before you'd see significant impacts. And then we have the current irrigated agriculture, which you can see is a lot lower. So we determined that Long Lake was impacted. Pleasant Lake, it's a much deeper lake, and so the significance thresholds were greater. Like you could come down further before you would have an impact to the ecosystem. And then it turns out that the irrigated agriculture didn't bring it down that much. So that one we determined did not have a significant impact. So I'm not going to really go into this at all anymore, but I just wanted to give it as, this is a climate, environment, and people seminar, thinking about you can't really just solve some of these issues by themselves. Thinking about these groundwater withdrawals, if we had just ignored climate, we would have just seen all this variability and been really kind of confused by it. We had to look at the climate effect in its own, and then try to parse out the effect of the pumping. So I think that'll be really important for us as we tackle these sort of climate issues going forward, on top of, layered on top of all the other sort of anthropogenic impacts that we have. This is just an idea for going forward. That was a really multi-million-dollar study that took years to do, and 30+ scientists. If you don't have that, maybe just something simple like the bathymetry of the lake, you could look at and see, how likely might that be, this lake, how sensitive might it be to a reduction of lake levels, either because of climate or because of pumping or some other thing. So this is just showing you a shallow lake that you could imagine, yes, with a little drop in lake levels, you can see this gradual slope. You would see the lake shoreline recede dramatically. And this is showing you the maximum depth of a lake and the percent volume loss if you drop the lake 1 foot. And so again, you see in these shallow lakes, you know, they're very sensitive, and then once you start getting down up to the big deeper lakes, they would be less sensitive. And so this is in the central sands area, again, using that percent volume loss at 1 foot drop as an indicator of how sensitive some lakes might be. And you can see that, you know, you could have here red being, you know, more sensitive and yellow being less. You could have some right next to each other that would have different sensitivities, just based simply on the bathymetry. So, yeah, I think this lake level management is something important for us to continue to think about and work on. So here, expanding lake level monitoring across the state, continuing to develop and improve upon these modeling efforts for places where we don't have lake level data. And then we can define the natural lake level regime and look at impacts, be they physical, like, you know, water clarity, or biological, like the mercury bioaccumulation, set management targets, and then regulatory policies for managing water quantity. All right, now, I already kind of talked about this, but so I think really for us to understand how water budgets will change in the state, that's really important. Nailing down kind of this evaporation effect versus precipitation. This was a paper done by Delaney and others looking at climate vulnerability in watersheds in the upper Midwest. There's a new study done by Dale Higgins from the Forest Service that's hopefully going to get published really soon, in which he looked at which watersheds in the state are the most flood risk, have the most flood risk basically. So when there's streams, which ones will have the flashiest sort of response to one of those extreme rain events. So looking at things like slope and the soils, those sort of things were important. So that would be great when that comes out. And then helping to just define the expected lake level fluctuation for people so they kind of know what to expect, and we can talk about it more. Yeah, I mean, we just get a lot of calls, like the lake's really low, I want to fill it up, or the lake is getting really high, can I drain it out? And just trying to get away from that sort of language and expecting a stasis, to realize that this is natural, and then also with climate change it's going to be maybe different than what we've seen in the past. So I know maybe I should be closing out soon, so I just wanted to talk to you about a few adaptation strategies that we've been looking at. Really, adaptation is, you know, trying to adjust our systems in response to climate change, and really to try to meet our goals and objectives. So I talked about climate change. We got warmer temperatures, more extreme rainfall. I didn't even talk about all these impacts today, but yeah, I talked a little bit about cold water fish, harmed infrastructure, more extreme lake levels, but there's these other impacts too. There's a lot of adaptation actions we can do, and one of the points that I wanted to make is that we're already doing a lot of this. It's just part of water resource management, trying to maintain good water quality. And so I think we need to continue doing this, and then it just really makes it even more urgent. So reducing nutrient loading to our water, you know, in our watersheds, protecting and restoring wetlands, enhancing water storage, reducing storm flow, all these sort of actions, and more. I just want to end this is kind of wearing my wiki hat again, thinking about different adaptation strategies. They can be sort of resistance sort of things where we want to try to maintain the condition as is. So I was talking about cold water fish. We want to try to still maintain them in lakes, but then accept would be more of accepting the new condition, but trying to manage for it. So here's a swimming beach in one of the Madison lakes with a filtration system. So recognizing we don't have good enough water quality for people to safely swim, so we'll just make a barrier and clean the water. Direct is more like where things are going to change, and we want to try to have an influence on what that outcome will be. And so this is our fisheries actually at DNR isn't really doing this now, but there's conversations, and I think it's just an illustrative example where you could be recognizing, again, like let's say one of these lakes is warming up, it's not really going to be a great fishery maybe for Cisco anymore, so what kind of fishery are you going to promote there instead? I think we can also kind of couch our different adaptation actions in terms of sort of policy sort of decisions. We can go at it with zoning regulations or putting incentives out there for more water infiltration. We can take the engineering approach, again, maybe for water infiltration, or making sure that our stormwater infrastructure is well built, for these bigger storm events. And then, of course, to protect, the conservation side, like protecting and restoring wetlands. I just had two specific examples on some ways that we might think about adapting at DNR. This is some work that my colleagues are doing. This is not the work I do, but we have total maximum daily loads. These are basically prescription, if you will, to make sure that we lower the amount of phosphorus going into our streams and lakes. And so these depend a lot on running these models and coming up with the phosphorus concentrations that wastewater facilities can discharge. Depend a lot on the rainfall data. And so the rainfall is changing, so what should we do? DNR is interested in using NOAA's developing this new rainfall statistics with Atlas 15. So basically starting to apply that to the TMDL models instead of using the old precipitation data from the past. And then I think one of the take-homes here is that we might just have a shorter shelf life for these types of restoration plans. You might have to update them more often as things keep changing. This graph on the right is just showing you the phosphorus load for the Kiwani River, and basically just that one of the key points for a lot of these studies is that a lot of the phosphorus load is coming in with just a few of these extreme rain events, so that'll be really important. Then the other one related again to that NOAA's Atlas 15 rainfall statistic is being really important. Another application is for our stormwater infrastructure and being able to use, instead of designing the engineering designs for culverts and stuff like that, instead of designing for the storms of the past, starting to design for storms of the future. But this is not, again, not my forte, but what rainfall statistics do you use then? And so this NOAA's Atlas 15 is something that DNR is looking toward, and then trying to provide technical assistance to people when they need it. So I'm gonna kind of close out just by pointing out, like if you go to our wiki website, you can see a lot of great stories and examples of the kinds of adaptation actions that people are already doing. So check that out, and then I'll just end by with another quote from Edmund Toten, that I make more impact at the local level than at the higher level, and I think that is really important for us here in Wisconsin to think about, that here we can work on the systems that we have here and try to make a difference. So I think I'll stop there.
Great, great. Thank you very much, Katie. Really enjoyed the presentation. Thank you. We do have time for questions. If anyone has questions for Katie. And we may have some online as well.
We do have a question online that I could kick us
Sure.
off with.
Yep.
Will hotter temperatures promote algae in Wisconsin lakes, which you touched on briefly, and what are the mitigation methods?
I think, the literature is kind of showing that, the warmer temperatures favor cyanobacteria. And I can't really speak to, there's a really great paper by Pearl and others that talks a lot about some of the different mitigation strategies. Of course, we could go with, I just keep looking at you as you ask the question, but of course you can do, we continue to do things, work in the watershed, reduce nutrient inputs, but then there's some other ideas out there, I think, for more of the engineering side.
I'm going to ask a question if I may. So maybe more towards the front end of the talk, you were talking about healthy aquatic ecosystems, and so maybe it's fish, and so we talked a lot about temperature and dissolved oxygen, but then let's say, phosphorus or extreme events leading to more phosphorus. If you had a magic wand and you could just eliminate one of those things, so we'll say increasing temperatures or increasing or continued nutrient transport into the lakes, which one would you choose? And I guess what I'm getting at is one of those, they're totally intertwined, I get that, but is one of those maybe more detrimental to, in general, to aquatic ecosystems? So if you could just do away with it,
I
but you
think
could
I'd
only
still
choose
pick
one?
phosphorus.
Okay, okay. And is that good because we maybe have more control locally over phosphorus than we do over temperatures?
Yeah, maybe. I mean, it'll be interesting, I guess, to think about that more, like in our forested watersheds and in the north where, maybe it's not phosphorus so much, but thinking about the browning and the warmer temperatures and the ice cover. I think I maybe also just haven't thought about that, those aspects of this.
Okay, yeah, I like that answer though. Other questions?
Katie, I'm curious to what extent DNR uses citizen science as part of its programs in Wisconsin and even in the Madison area. I know we have UW here in Madison, so plenty of scientists to go around. But just throughout the state, citizen science has its,
It's
pros
like-
and cons, but it's great. It's great in many ways. So just curious how DNR works with citizens.
I could have talked all about that, only. I would say it's the backbone of our monitoring, actually, for water quality monitoring. We are kind of, just put out some numbers. We have over 800 volunteers that do water clarity monitoring every year. We have over 500 that do water chemistry. They do phosphorus and chlorophyll on our lakes. That is where we get, and our staff monitor about 60 lakes. So we get most of our data that we use for assessments and looking at trends from volunteers. And unlike a lot of other states, we use that data as if it was from our scientists. We have training programs, we have them do duplicates and blanks, and we do the quality assurance, and then we put in our database with everything else and use it for assessment. So it's super important, and I don't work on the streams as much, but we have a Water Action Volunteer Network as well. And again, there's sort of layers of like more intro level, just doing some basic things, and then we do have volunteers collecting phosphorus, which goes to help with those TMDL plans and everything too. So, yeah.
What's your background, or how did you get into this job and position?
I am from Madison area. I did my undergrad here at Madison in zoology, and then I got involved I was a senior for my senior thesis. I did a study on Sparkling Lake up at the UW Trout Lake Station. So that was I actually got kind of introduced to that through Zoology 152 at a research part. So that's how I kind of got to know some of the professors. Then I was doing my master's up there. I really wanted to work in the tropics, so I decided that I should get a PhD so I could work in the tropics. So I went to Utah State and did my PhD there. Then I did a postdoc in Sweden because I thought that would be fun. And then I was really, I was looking at academic track or other tracks. I wanted to come back here, and so I ended up with the job at DNR. And I don't know if there's more to it. It's kind of some really like important things in those decisions. Like I want to go to the tropics, I want to travel around, I want to be closer to family again.
Good question. Any other questions? All right, great. Well, let's thank Katie again.